So what we did so far is getting a point estimate for an unknown parameter, right? But that's just one single point estimate. So what we want to come to now is, what if we want to have an interval of feasible values for the unknown parameter? And that's referred to in the literature as a confidence interval. Yeah? Or what if we want to assess the uncertainty that comes with the estimator that we put together? This kind of questions, right? So you want to go beyond the single point estimator. And in general, we will have to rely there on some approximating results. So we'll have to rely on the whole nice theory that is developed for the maximum likelihood estimator, on the whole asymptotic theory that is developed for that. And this is also the advantage of using the maximum likelihood estimating framework above other frameworks. And we discussed the moment estimation method earlier on in this chapter. So here with the MLE, you have this nice framework that will give you insights in, for example, the variance that comes with your estimator that you derived. Yeah. So I mentioned this. So far we focused on point estimators. You've got a single value that represents your best attempt to determine the value of the unknown parameter. And now we want to come to an interval estimation meter. Yeah, so that gives you then a range of possible numbers, any of which is likely to be the true value. So this, if you would frame it in the language of a modeler, an actuarial risk modeler, you would say here you're going to try to assess some parameter uncertainty, right? So I think we touched a little bit on that earlier on. So when you look at different sources of uncertainties, when building risk models, you can talk about process uncertainty, you can talk about parameter uncertainty, you can talk about model uncertainty. So what we're now really going to look into is how to capture this parameter uncertainty if you can rely on the toolbox of maximum likelihood estimators. Yeah. What we refer to with the process uncertainty, that's really the uncertainty that comes with the distribution that you assume. For example, if you work with a Poisson, you can take a random draw from this Poisson. So there will be randomness coming in like this. Parameter uncertainty would then come from, yeah, if you work with a Poisson, instead of working with a single lambda head value, you may want to pick your lambda parameter from a range of possible values. So then you try to quantify this parameter uncertainty. And then the model uncertainty, that's coming from, yeah, but why do you go for the Poisson? Maybe you want to go for a negative binomial or some alternative models there. So each of these choices and specifications comes with its own source of uncertainty and randomness. So here a very difficult slide, and I forgot to build in transitions, but what if we look at the random sample, say x, so x is a vector, so that's x1 up to xn, the sample that we collected. Let's assume that this comes from a probability distribution with certain parameters theta, which we need to estimate, and then perhaps also some other parameters phi, which we're not immediately interested in. If we then write down a confidence interval for the parameter theta with a certain confidence level gamma, say for instance 95% or something. So what we're then looking for is to put together an interval with random endpoints. So the endpoints should be a function of the random vector x, such that the following property holds. So the probability under the assumed model that theta is within these endpoints, that should be equal to the gamma level, the 95%, for example. And how would you gain some intuition for what this means? It means that if you would draw alternative samples from the model that you assumed, that then the fraction of calculated confidence intervals, which encloses the true parameter value theta, that fraction of intervals would go to gamma times 100%. And it's a big statement, but I try to visualize it with a picture from somebody else, but I try to picture it like this. So let's say that you try to put together a confidence interval for the mean, that the true mean is at the dashed line. Then what these confidence intervals will tell us is that if you repeat the experiment, in this visual, we repeat the experiment 10 times, so we get 10 different samples. For each of the samples, we calculate the confidence interval for the true mean parameter, right? And then we'll see that in this case, how much? 2, 4, in this case, 6 out of the 10 intervals include the true mean parameter, right? And if you repeat this experiment a lot of times, you'll see that 95% or something of your constructed confidence intervals will include the true mean. That's a bit the idea. Okay, so we want to put these intervals together. So we want to get our grip on the variance of the MLE and on the asymptotic distribution of the MLE, right? And then you are really entering these big results from mathematical statistics that we're only slightly going to touch upon, but which we need to understand to a certain extent in order to make sure that we can get a bit of grip on how we would quantify the variance of our MLE, of our maximum likelihood estimator. So here what we're going to say is that if you look at the distribution of your estimator, you know that here with theta n, so we look at the distribution of the estimator, so that means I'm going to approach my estimator as a random variable, yeah? Then that converges to a normal distribution with as the mean the underlying true parameter theta, and as the variance, you get the following result. So if you really want to know the variance of the theta hat of your maximum likelihood estimator, you should work with the inverse of this calligraphic I expression, and that is the Fisher, the so-called Fisher information matrix. So we learn a couple of useful things from here. So we know that the MLE, if I let n go to infinity, so if I'm able to collect more data, then my MLE will be unbiased eventually. And unbiased means that it will converge to the true unknown parameter that I try to estimate. And I also know that asymptotically, so if I take the limit for n going to infinity, that my maximum likelihood estimator will follow a normal distribution with this variance captured by the Fisher information, by the inverse of the Fisher information matrix. Yeah. So for us, the result at the bottom is important. So we get, by inverting the Fisher information matrix, we get this useful approximation for what the variance will be of our maximum likelihood estimator. So we're going to use that result if we want to put together an interval of possible ranges for our unknown parameter theta. Now the clever readers or listeners may say, yeah, but what you write here, it's only valid if you're looking at a single parameter theta, so that's correct, right? So this is the setting for a single parameter. We're going to generalize to the case where we have multiple parameters that need to be estimated later on. Okay, so let's take a moment to look at this Fisher information matrix. So you will see that in different forms in the literature. So the authors of the book, they put an n in front, and sometimes you see it with the n or without the n, or you see it written for the log likelihood, whereas here we write it for the log density. So these notations slightly differ. So we're going to stick to this one. And what we have in this Fisher information matrix is we look at the expected value of the second order derivatives. Yeah, and it's the expected value with respect to the distribution of the random variable x that we're assuming. Yeah? So one of the first things we're going to do is we're going to reflect upon what are different ways to write down this this Fisher information matrix, because you'll see some other ways to put that together as well in the like we mentioned on the sheet. So what we're going to do is we're going to look at minus n times the expected value and then the second order derivatives of the logarithm of the density. You know, so the thing I'm going to put into my likelihood. Okay. And what I could recognize here is, so there is this minus. There is this minus here. We got the expected value here. And what we got here is the second order derivatives of the log likelihood. Or in this case of the log density, because somehow, well, sort of I'm assuming that if I have an IID assumption, that then my log likelihood reduces to n times the logarithm of the density under consideration. So these concrete specifications sometimes differ. So sometimes you see it written as a function of the log likelihood. Here it's written as a function of the log density. Yeah. Now this second order derivatives of the log density, we also refer to that as the Hessian, right, in numerical routine. So that will be important later on when we're actually going to do this on specific examples. Now, one of the properties of this Fisher information matrix is that you can show that you can also write it as follows. So n times, and then the expected value of the product of the derivative of the log density, and in this case with itself, so to the power 2, right? So that's a property that you often see coming up. So I took a moment on the shades, and that's sheet 31, where I'm writing down this equivalence between both expressions for my Fisher information matrix, either by going through the second order derivatives of the log density or by working with the first order derivatives squared of this log density. So I'm just going to take a moment to show what I did on sheet 31, because I think otherwise it's maybe a bit of an obscure notation there, or an obscure reasoning. So let's take a moment to convince ourselves that this equivalence makes sense. And keep in mind, the reason why we do it, the reason why we bother about this Fisher information matrix is because if we look at the inverse of the Fisher information matrix, it's going to give us the variance of our MLE estimator, right? So that's why we do it, because we want to quantify this uncertainty that comes with the maximum likelihood estimators that we calculate, right? So this is why we do it, because in the end, we want to have, it's going to be a matrix if you work with multiple parameters that need to be estimated. So in the end, you want to be able to invert this matrix to get a numerical quantification of your uncertainties that come with the maximum likelihood estimation technique. Yeah, so that's why we do it. So let's take a moment to think about the reasoning, the one that I have over here. Why would this make sense? In the case, I'm going to do it in the simple case where I've got a single parameter coming up. Yeah. So if you look at the reasoning on sheet 31. So what we're going to do there is we're going to start with the second order derivatives of the log density. Okay. And if I think about that, I can see it as follows. It's the derivative with respect to theta of the derivative with respect to theta of the log of the density f that I'm using in the proposed model, right? But if I work out this this first derivative that you see over here. So if I take a step to do that, then I'm actually going to work with the derivative with respect to theta of 1 over the density times the derivative with respect to theta of the f itself, right? And if I look now at taking the derivative with respect to theta, then I need to work. With a product of two functions, right? So this should match. So if I work out the next derivative, so what can I do? Well, first of all, I could say it's 1 over f x theta, and then take second order derivative of the f of the density, right? And then I need to add to that the derivative of 1 over, and then multiply that with the derivative of f, right? So the derivative of 1 over the density, that's going to be minus 1 divided by the density squared. And I need to take 1 times extra the derivative with respect to theta of the density. But I already had that, so I'm going to get that twice. Okay. So it's a bit complicated, but and I hope I didn't make a typo. But what we're doing here is, in the first line, you need to take the derivative of a product of two functions. So you're going to apply the rule for taking the derivative of a product, and that's what's going on over here. So if I write that in a more concise way, I could say it's the second order derivative with respect to theta of the density divided by the density itself, and I need to subtract minus the derivative with respect to theta of this density squared, and I'm going to divide by the density itself squared. That's what I've got. And this last step, I can even write it in a bit of a simpler way. I could say this last guy over here, so this whole thing, I could also see that as the derivative with respect to theta of the ln or the log of the density, right? And that squared. Because if you're taking the derivative with respect to theta of the logarithm of the density, you'll get 1 over the density times the derivative with respect to theta of the density itself. Okay, so this is a compact, or this is what I get at this point if I'm starting from these second order derivatives of my likelihood, of my log of my density in our case. And if you look back at the definition of the Fisher information matrix, what we need to do now is we need to take the expected value of this thing. So we need to take the expected value of this thing with respect to the distribution of the random variable x. So we're going to wonder, yeah, you've got two terms here in the expression. If you look at the expected value, what's gonna happen? And we're going to look particularly at what's the expected value of this guy. If you consider x to be a random variable, then what's going to be the expected value of this guy? Okay, so let's do that. Now, think about the expected value of the second order derivative of the density divided by the density. And I just want to show you, to give you a bit of a glimpse of how these steps go. I will not ask any theoretical exercises or problems or whatsoever that hint upon these kind of reasoning. But in the end, I want you to be able to apply it, right? To be able to write down a confidence interval for an unknown parameter. But let's just force ourselves one time to think about what the underlying reason is. So what you see here is same principle as always. This is a function g of a random variable x. And if we need to calculate its expected value, so what we're going to do is say g evaluated in x multiplied with the density of x dx, right? That's what I'm going to do in general. So now let's plug in the expression that I've got. The expression that I've got for my function g. So that's my second order derivative. I'm going to divide by my density, evaluate in the value x. I'm going to multiply with the density evaluated in x, take the integral over all values x. So these guys cancel out. I've got an integral of a derivative, right? So under certain regulation, under certain assumptions, I can assume here that I can flip the order of the derivatives, the partial derivatives here, and the integral. And then I'm left with the integral of the density over all values of x, but that's then equal to 1, this integral. So the derivative is going to be equal to 0. So if I return to my original expression, or the expression that I obtained so far for this, if I return to the expression that I obtained so far for the second order derivatives of my log density, if I would take the expected value, then I will see that this term is going to drop from my expected value. I don't need that. So I'm left with minus the expected value of this guy, right? But that was exactly the definition that we gave for, or not exactly, but that's the definition we wanted to work to for our Fisher information matrix. So what we can decide now is that, if I look at final step, so in the end, if I'm writing down minus n times the expected value of the second order derivatives of the log of my density, right? Then due to the reasoning that I build up, I can say that that should be equal to minus n times, and then I've got an additional minus 1, and I've got then the expected value of the derivative with respect to theta of my log density, this one squared. And that's exactly the alternative specification for the Fisher information matrix that I wanted to consider, right? So if you look back at the sheets, these were the two equivalent specifications for my Fisher information matrix that I wanted to investigate. And the reasoning that I build up is by starting from this expression, working it out more concretely, then bringing in the expected value, noticing that by taking the expected value, one of the terms that I end up with here would drop because it has expected value equal to 0. And so the only part that is left, that's the part where I'm working with the expected value of the first order derivative of the log density squared, right? So this shows the equivalent expressions that we give for this Fisher information matrix. So I know it's complicated and it feels super theoretical, etc., etc. All of that is true, but I wanted to give you a glimpse of this kind of reasoning, this looking under the hood for once, right? Okay. Any questions? All of this is for a single parameter. So one of the next things we want to do is what can be done if you have multiple parameters. So what would the expressions then become? So that's what we're going to do here. So if I return to the sheets, do keep in mind, this is the reason we're doing it for, because we want to get our grip on the variance of the maximum likelihood estimator. Then we need the inverse of the Fisher information matrix. And we derived two representations for this Fisher information matrix. So this is what we did on the iPad. And in the end, we concluded for a single parameter under certain regular, I cannot find the word, under certain assumptions, I can write this Fisher information matrix in one of these two equivalent forms. Yeah, so that's what we obtained so far.